Hi everyone, welcome to the first one of another semester of ZX seminar talks. This week we have Boldizsár Poór, who will kick us off with a talk on Floquetifying stabilizer codes using distance-preserving rewrites. Please, Boldy.
Thank you. Yeah, as John said, I'm going to be talking about Floquetifying stabilizer codes and distance-preserving rewrites. This is a joint work with Ben and Alex. Yeah, let's get started. So first of all, the motivation for this paper came from another paper from Teague et al., where what they did is they floquetified the color code, and this was done using obviously ZX calculus. So what they did is they had some kind of specification of is my cursor visible?
Yes, it is visible.
Nice. So they had some kind of specification of a quantum error correcting code. They did some kind of ZX rewrites in a smart way, and what they ended up with is a Floquet code. And we are doing something very similar, but we are going to be a touch more general in that we are going to be talking about stabilizer codes. And what our goal is to obtain a new code that uses only weight 1 and weight 2 measurements. And what we will also show is that the rewrites we use preserve certain properties. So from the title, you might already know that this is going to be the distance that is being preserved. We take a local perspective, and then we also, so preserving these regular properties, this is going to be quite well formalized in this talk. So for those of you who are not so familiar with quantum error correction, I'm going to just give you a very simple perspective. So here we have Alice and Bob. Both of them have some kind of quantum computer, and what they want to do is communicate. But when Alice sends qubits to Bob, something might go wrong and some big error happens, and Bob receives some information, but this is not the same thing that Alice has sent. So what we do in error correction is, instead of just sending strictly the data, we encode this data into multiple physical qubits, such that when an error happens, the redundancy in the amount of information we send enables Bob to hopefully determine what kind of information Alice wanted to send him. So in this case, this would be that we have some kind of data qubit, which we encode into a number of physical qubits. And even if an error happens, which is small enough compared to our code, we can still decode it and obtain the original quantum information we need. So interestingly, we only need to care about Pauli errors, so X, Y, and Z errors, and and maybe, a number of these. So here we have 3 of these errors in a row. So this would be one error of weight 3. We do not need to care about entangled errors, at least not in this talk. Okay, so just another quick terminology: Floquet codes, or we might refer to them as process codes. So what we have is we have an operation schedule, which is a list of operations. And then each of these operations is either some kind of Pauli measurement. It can be any weight Pauli measurement, so it could be a very big Pauli measurement as well. And it can be some Clifford unitaries as well. And what we do is we have this O, so this is a repetition of certain operations, and we keep on repeating this one after the other. And this is going to give us our process code or Floquet code. And that gives also us the operation circuit. So something to remark here is that while if we repeat this operation scheduled an infinite number of times. This is going to be error correcting code, but it is not the case in the very beginning. So, you have some kind of data qubits, and before repeating it enough times, this is not going to act as a quantum error correcting code. So that is what establishment means. So a circuit is established if the size of the instantaneous stabilizer group is not increasing anymore, and the distance. And the distance is the lowest distance of the instantaneous stabilizer group after establishment. Okay. We work with the usual qubit Clifford ZX calculus. So we have red green spiders or Z and X. We also have the usual Hadamard gate. Nothing special here. And we have just usual rewrites. So in this case, we have two circuits that are equivalent. Then we can two diagrams that are equivalent, and we can replace this diagram in a larger context with this other diagram that is the same as the one. So this was what I would assume most of you are familiar with. And another quite powerful tool that we have been using are called polywebs. So polywebs, they will be very important and quite powerful. And what's also hopefully new in our paper is we aim to formalize these polywebs. So we define them quite well. So given a ZX diagram D, a polyweb is a set of pairs, each pair containing an edge and a type, such that, and this is going to be quite complicated, a spider with a polyphase can have an even number of legs highlighted in its own color and or all or none of its legs highlighted in the opposite color. So I'm going to skip ahead and just give a couple of examples. So this is a poly spider, a spider with a polyphase. So it can have an even number of its legs highlighted in its own color. This is the first case. Or all of the legs highlighted in the opposite color is the second case, or the combination of the two, right? So we allowed and or. So these are the three cases we can have with polyphases. And then secondly, we can have plus or minus pi over 2 phases, which can have strictly either an even number of its legs highlighted in its own color and no legs highlighted in the opposite color, or an odd number of legs highlighted in its own color and all legs highlighted in the opposite color. So back here, these are the two cases we can have. So either even number of legs in its own color or odd number of its legs in the opposite color with the opposite color highlighted in all the other edges. And something to remark here is that there have been a number of publications that use polywebs, and if I am not wrong, there is one that uses the opposite convention. So the colors would be the exact opposite of the polywebs. So just note here, this is what we mean. And then just to have an intuition for these polywebs, they kind of correspond to firing spiders. So this means that for each of these highlighted edges, you can introduce a spider with pi, and this would be equivalent to the diagram without these pi spiders, because you can always fuse these together and then eliminate in this case, or in this case first fuse, and then you can kind of push one of the pi's through, which will then eliminate each of the others. Okay. And then the good thing about these polywebs is they correspond to well-known concepts in quantum error correction, one of them being stabilizers. So a stabilizer is a polyweb with no highlighted input edges. An example would be this, where you see that no input edge is highlighted by any polyweb. And in this case, this means that these polys or this poly string is stabilizing this diagram. Yes, it's very simply, that's it. Logicals are polywebs that highlight both input and output edges. And this is important in quantum error correction because what you have is you have some kind of encoder first with a couple of logical qubits which correspond to some physical qubits. And then what you can think about is if you have some kind of polyweb that highlights one of the edge and then corresponds to maybe these two edges, that means that the logical corresponding to this in the physical qubits will correspond to these two. So this is why this is important. And lastly, detecting regions are polywebs with no input or output edges. And a nice proposition we have is that a detecting region can detect an odd number of errors of the opposite color. And we have a nice proof for this. Just a simple example would be this. So let's say an error happens here. In this case, this is how our diagram looks with the error applied. Then according to the polyweb, we can fire each spider. We can commute the pies through one of the Z spiders and then get rid of all the other Z spiders. But the commutation introduces a -1 phase. And then if we look at the overall picture, we see that this diagram equals to this diagram. And in particular, A, let's say this is our diagram, is equal to -A, right? Because there is the minus phase. This means that A has to be 0. Okay. So these were all the concepts related to polywebs. And now let's talk a bit about kind of errors. So again, we have a newer notion of errors on ZX diagrams. And to define them, we first define an edge flip, which is in a sense an atomic error. It's kind of the most elementary part of an error. So an edge flip in a ZX diagram is just an edge where the error happens and the type. And we write D plus the error to denote the diagram with the edge flipped with type D. So for example, we have this diagram and if we add this error to this diagram, we get this diagram with the error. Some of you might have noticed that the type doesn't include Y. And the reason for that is because these are kind of the most atomic errors you can have. A Y error is going to be the combination of an X and a Z error on the same edge. And now let's define errors. So an error is just a set of edge flips. And we denote it the same way as we denote it with edge flips. And a couple of terminologies we use. So the weight of an error is the number of edges affected by the error. So this is important because of the Y error, which would be an X and a Z error on the same edge. Two errors are equivalent when their application gives the same interpretation on the same diagram. An error is trivial if it doesn't change the interpretation of the diagram. And an error is detectable if applying this error results in the empty diagram. So quickly coming back, this is a detectable error because it gives you once you apply it, the interpretation of the diagram is 0. So this is what we have seen here.
I'm sorry, Bolly, could you go back to your
Yeah.
final previous slides? Yeah, that one. Is
Yeah.
that final E, is that like a different thing
Oh, sorry,
than
this should be the curly E, yes.
Yeah, okay.
Sorry. Yeah, good point. Thanks.
I also have a question. So when you say the interpretation of a diagram, do you mean the linear map correspond to that? Or
Yes.
so you mean you're evaluating your diagram in terms of a matrix representation?
Exactly. So these definitions do use linear maps, but they are just kind of a convenient way to describe different ideas, because we could also maybe say that the full reduction of the diagram gives you the same diagrams, but we thought that the cleanest way to express these ideas would be with linear diagram. But yes, that is indeed what they mean. Might be a bit unconventional, but they do work quite well.
And so can you go back to the previous slides where you have the detectable region, like the example? Right.
Yes.
So I wonder, what if you have a more complicated diagrams where the connectivity between spiders are more than just this? Is there a way for you to, because now you're doing diagrammatic rewrite, and because it's simple, so it's easy for you to get -1. But what if you have a more complicated diagram?
So we do have a proof for this. It's going to be a very similar process to it. So when you have an error, you have some very complicated diagram with a lot of connectivity, and you have an error here that you can detect. Maybe, not just a single, but a number of them. But what you will have in the end is that this is simply just commuting through the errors with these with the pi phases introduced by firing, and it does give you the -1. I feel like this is the easiest way to talk about this. We also had an interesting way when we tried to use a lot of local complementation and pivoting to derive the same idea, and then later we found this proof, and it's much neater. But yes, the idea is just about commuting an error spider, a spider corresponding to an error with the ones that come from the detecting region.
Thank you.
And then but I do see that this might not be obvious from just this diagram, but do you look at the paper? I think we have a nice explanation there. Okay. Okay, so ZX distance. So now we have defined what an error is on ZX diagrams. Let's look at distance. So we say that a ZX distance of a diagram is the minimum weight. So just remember, a weight was the number of edges affected. Minimum weight of all non-trivial. So a trivial error is something which doesn't do anything. So non-trivial is that changes the interpretation, and undetectable. And undetectable was something that would, so undetectable would make this not equal to 0. So the minimum weight of all non-trivial undetectable errors is the ZX distance. And then we have a number of propositions. First, that given a process code or a Floquet code, the ZX distance after establishment is at most d. So the ZX distance is at most the distance of the process code. And for stabilizer code, it turns out that the ZX distance is the same as the distance of the stabilizer code. Okay, so if anyone has any questions, this is a good place to ask. We have kind of gone through all the preliminaries to go into a bit deeper ZX-based.
I have a question about the logical operators. Could you maybe go
Okay.
back to that slide?
Yes.
So in the logical operators, it intuitively makes sense to me like that this kind of means that if you apply the operators according to the Pauli web afterwards, that would mean doing that logical operation. So you have some input to the Pauli web and some output, and that's like the old code versus the new code. Logical operator. What I don't understand is what about the edges that end inside of the diagrams. So here, for example, the one at the bottom that ends in the red one. How do we
This
interpret this? No,
This one.
the one below it. Yeah, that one. Yeah, the one that is
Okay,
not an
so
output.
that is a very good question. So this one, in this case, is a bit fabricated example because this would just copy through, which would be quite different. But in real world, sometimes what you have is encoders of the form. So this is a green spider, and this is a red spider. And what you might have is some kind of connectivity here with the same number. So let's say n. Might be nicer with k, but n is fine. So some connectivity here, and then you might have some further connectivity here. So this is kind of a general way in which encoders may look. So in a real world example, you wouldn't really end up with anything like this. What you might also have is some further connections here. But yes, I see this this kind of example is not going to be present
So
in real world examples.
you're saying in a real code, your Pauli web would never end internally.
So you might have edges where this kind of stuff happens. For example, if you translate a quantum circuit into a ZX diagram where you have state preparations or destructive measurements, single qubit measurements, then you might end up with something that looks like this, of this shape. And you might have logicals or stabilizers or whatever that kind of end in these. One way to look at this is that so if you take any cut of this logical, no matter where you place like Paulis of that color on all the qubits that are highlighted, on all the edges that are highlighted, you're kind of doing the same operation. So you could either be doing this operation at the very beginning on the input. You could also be doing it in some intermediate cut, or you do it at the very end. All of this, in effect, will give you the same diagram. And in particular, with these edges that go into a measurement or a preparation, whether you do something there or not doesn't really matter because it's then stabilized. If you do a Z operation after you've prepared a state in the opposite it is stabilized. This doesn't make a difference. So you could put the Pauli there. You could also just kind of move the cut a little bit further and only have the two outputs where you do something. This does actually not make a difference.
Yes, thank you.
Okay.
Very good. Any other questions?
So can I ask about the definition of detectable error?
Yes.
I didn't quite get why it's right to say it's detectable if its meaning is 0 rather than
very good question.
It's not rather than saying it's detectable if the semantic of D plus E is not the same as semantic of D.
So okay. Here, I think not just here, but throughout this talk, I have been a bit cheeky in that I haven't told you that what we do is we post-select on the outcomes of certain measurements. And this is the reason why this definition of detectable error makes sense, because what we do just coming back here, is you can think about this as a two-weight Pauli measurement and this as a two-weight Pauli measurement. And what this means is that you have already post-selected on the measurement outcome 0 both times. So this means that the same measurement outcome happened, right? And in this sense, if you post-select on both, then an error happening between two and giving you the same result has the probability of 0. The other thing you said was, why doesn't it kind of, that D plus some kind of error changes its meaning, so it's not equal to D. Sorry, this is not really fitting here. So why don't we use this? So first of all, when it's equal, it's trivial. So when is it trivial? Either when you don't do anything or you do something that stabilizes your diagram. So what we are saying here is we do something that doesn't. So it's not necessarily true that it's going to be detectable if it changes the diagram. I could imagine.
Do you mind if I jump in here?
Yeah.
So the way I like to think about this is when we think about detectable errors, we're thinking about detectable with certainty. So if you think about what this diagram represents, this diagram represents doing some gates and some measurements where the measurement outcomes are always 0. And we think of 0 as the error-free outcome. Okay, so if I run my circuit and I get outcome 0 in all my measurements, that's telling me that no error had occurred. Okay, so that's like if I got no error syndrome. So now an error is detectable if the probability of getting no error syndrome is 0. And that's exactly what this last bullet point is saying.
Okay. Yeah, I see now. Yep.
Thank
Hi,
you.
sorry. What does this mean physically, like in an actual device? Because it seems like you have very different definitions to like a conventionally defined in error correction literature.
I'm going to answer this quite quickly. So it's going to be very different than a physical device, because in a physical device, you would have some kind of ZZ Pauli measurement. Then something goes wrong here on the top qubit, and then you do another ZZ measurement, right? Z. And both of these ZZ measurements give you some kind of bit information about the parity of your measurements. So here we post-select on 0 and 0. But this would not be the case with an error, right? Because if you have measured 0 here after the error happens, this measurement would give you a 1 as the parity. So the parity changes.
So this
I
is
hope
a
that-
detectable error in your definition.
Sorry, which one?
So what you just described when the parity flips and the syndrome
Yes,
is basically
yes, that
one.
would be a detectable error. That would be another pi error here.
Okay. Thank you.
Yes. And while I would love to answer more questions, I see that I'm running out of time, so I'm going to just keep on going. So a very interesting definition we have is distance preserving rewrites. And to just give you some motivation for it. So let's say we have this 4-weight Pauli measurement, which is implemented as this ZX diagram. And we want to kind of extract a a circuit out of it. So what we do is we simply fuse this spider and then interpret it as a quantum circuit. Now, the problem with this is that if an error happens in this rewritten diagram, that is a single error happens, it's going to correspond to 2 data errors, right? So one error corresponds to 2 data errors. So this is what we would call a distance reducing rewrite, right? You had some kind of rewrite, and then this reduced your distance. And based on this, or motivated by this, we define a distance preserving rewrite as something that preserves the distance after rewriting from D1 to D2. And then from this example, we already see that the general fusion rule is not going to be distance preserving, but some rules might be, as we will see a bit later on. So another definition we have is distance non-reduction. And in particular, we have a proposition that shows that this, what we are describing here is equivalent to the one we have seen before. So a rewrite is distance non-decreasing if for any two diagrams, D1 and D2, that are rewrites, D1 to D2, an error E2 in D2 is either detectable or there exists an error E1 in D1, which is smaller than E2, and both of them give the same interpretation. So just, R rewrites D1 to D2, but if we do these rewrites with an error applied, there is another error which is smaller of size. And then distance preservation.
Sorry,
Yes.
Boldy. If I'm not forgetting my definitions, something is undetectable if the interpretation becomes 0, right?
Yes.
So are you here saying, because like in the first case they're detectable, so the second case is only relevant if it's an undetectable error, this E2? So then
Yes,
you're
exactly,
saying like
yes.
both these interpretations have to be 0, essentially, right?
It's detectable if it zeroes out the diagram. Not, I think you have a.
Oh, undetectable means it's non-zero. Okay, yeah. I got
Yes.
the thing wrong. Okay, yeah, makes sense.
Good. Okay, and then distance preservation is a rewrite that is distance preserving, and its inverse is also, distance. So so the rewrite and its inverse are both distance non-decreasing. So distance non-decreasing goes both ways. And then let's look at a couple of simple examples. So the first one, which is a very simple example, is just the elimination or the identity rule. So if we have just a single spider with 0 phase, then it's equal to the identity wire. And this is distance preserving. Why? Because any kind of error we place in this diagram or this diagram will correspond to the same number of errors. A bit more interesting case is this one. So we have some general Z spider, and a distance preserving rewrite is when we unfuse an empty spider from this. And the proof is, again, quite simple. So what we only have to consider is errors on internal edges, internal being not at the boundaries. So we don't have to consider errors here or here. So the only error we consider is one that may happen here. So first, an X error is stabilized by this spider. And then we see that this is actually distance decreasing. We have a Y error, then the X part is stabilized, and the Y part we can push out to the output. So this is distance preserving, and then again, this is distance preservation the other way around. Then another special case of fusion would be this R5 rewrite, where we replace this star with this kind of cyclic set of R three-legged spiders. And so the previous rewrites we didn't need to consider detectable errors, but here we actually can think about them because there is a detecting region. So any odd number of errors is going to be detectable. So a single edge flip we don't need to care about, or 3 edge flips we don't need to care about because they must be detectable. So we only have to care about even number of errors with even weight. And then what we can do is if we have 2 errors that are next to each other, we can just push the 2 out. In this case, we can similarly push them out, and then there will be 2 pi spiders here and here, which will be eliminated. And lastly, if we have 4 errors, then we can apply this 2 times and then get 2 errors out of it. Okay. And so we have kind of seen that we can do this for R5. So rewrite on 5-legged spiders. We can also do it in 4-legged spiders. And it turns out we can do it on even and odd-legged spiders from 5. So this is, for example, an even number of outputs. So this is the rewrite. Here, I'm not going to show you the proof. It's quite a bit more involved. So what we do is we kind of describe the detection matrix of this diagram and reason about the null space of this detection matrix. But in the end, it does come out really nicely. Okay, so we have a couple of distance preserving rewrites. And coming back to the original goal, so what do we want to do? We want to Floquetify a stabilizer code. Sorry. Not a color code, we want to rewrite stabilizing codes. And the kind of operation we want to have are C measurement, X measurement, preparations, arbitrary Clifford diagrams, C naught, other way around. So this is something that some of you might not have seen. This is just a ZX diagram that looks like this. So this is a weight 1 Pauli measurement. And this is the color flip version, and this is a weight 2 Pauli measurement. So this would be kind of the usual style we have seen before. So these are the kind of operations we want to extract. So the original paper had the same kind of operations. So this was so originally it had some kind of large Pauli measurement, and it rewritten it to something with small ones. And then to do this, well, we define a new notion of flow. So I'm just going to go back so you don't have to look at this ugly definition for a bit. Flow is something that people have used to kind of reason in measurement-based quantum computing about the way information propagates through your diagram. And it's also have been shown to be useful for circuit extraction. So in this case, we define something similar, but only for the purposes of circuit extraction. And this is quite a bit different than what you might have seen before. But at the same time, there are many things that are similar to the original definition of just a simple flow. So as usual with the flow, we have some kind of partial order. And here we take another approach where we have directed paths. So this is similar to something that Neil has done before in a paper showing the equivalence of kind of directed paths and the usual successor function definition. In our case, the directed paths are just a nice way to describe these things. So the directed paths respect the partial order on the vertices. Each kind of element in the directed path is, and so this is a bit complicated. This is, and for each neighbor of y, so each neighbor of the successor, such that the z goes to y. So I think this is easier to just draw it. So we have a couple of nodes. So x goes to y, and this is x, this is y, and then z goes to y, z goes to y. What we have to have is x is preceded by z. But only if x goes to y, and then in the neighborhood of y, such that there exists a j, such that this is part of the path, then x needs to precede z. So this is kind of saying that there is a pre-order, a partial order between these two when there exists a path from here to here. The rest I am not going to explain because I see I'm running out of time, but the point here is that this describes kind of diagrams that that fit our purposes. And then we have one more part of this definition is this well-coveredness, which says that no path finishes or ends in internal Z or X spiders with degree at most 1, degree more than 1. But we allow paths to finish here because this corresponds to just a measurement. Okay, and then in the paper, what we show, I'm just going to give these here as propositions, is that if we have a ZX diagram with a measurement circuit flow, then we can distance-preservingly synthesize a new ZX diagram with a well-covered measurement flow. So this means that if we have these properties given, then this property can also be synthesized. The next proposition we have is if we have a well-covered, so if we have a ZX diagram that has a well-covered MC flow, and the maximum vertex degree is not larger than 3, so this is very important, then we can distance-preservingly extract a circuit consisting of only the desired gates, as the desired gates as being the one I have shown you a couple of slides before. So these 2 qubit operations and local Cliffords. And based on this, so this is just an example that if we have some ZX diagram with an MC flow, which can be with a well-covered MC flow in this case, which can be described by a set of paths, then we can rewrite it into something that can be extracted into the desired gate set. And then lastly, if we have a ZX diagram with just simple MC flow, so this is not well covered, then we can find an equivalent ZX diagram with a well-covered MC flow, where all spiders have degree at most 3. So this means that this is, if we have any diagram, D, that has MC flow, so we have D, then we can extract a circuit which has a well-covered MC flow and maximum vertex degree not larger than 3, using which we can again extract a circuit of the desired gate set. So this effectively means that we can always extract a circuit if a ZX diagram has MC flow. The circuit extraction is based on these distance-preserving rewrites. I am not going to be going into any more details, but this is the R5 we have already seen, and this was Rn for even number of legs. And we have another, and this was the fusion rule. The second one I think I have shown. And these are the ones we use for the circuit extraction procedure. And kind of what happens is that we decompose, and we always get smaller and smaller and smaller spider in terms of degrees. And then in the end, we either end up with this or this rule, giving you vertex degree at most 3. And the MC flow is always preserved with these rewrites. Okay.
I have a question.
Okay.
So can I understand that at the beginning you said the Floquet code was defined by a infinite number of measurements, like Pauli measurements, O1 to ON, and then you're
Yes.
saying that you represent every non-destructive measurement in terms of ZX diagrams, and then you can find the circuit extraction, which is assisted by this well-covered MC flow, so that you can extract a circuit that will allow you to do the encoding process. Is this correct?
What do you mean by the encoding process?
Or like you will find the circuit that represent the Pauli measurements, but that is distance preserving, so that the error will
Yes, I
not.
think you have described it well, yeah.
Okay.
Yes, so we have something with high degree Pauli measurements. You have seen all these tools we have. We apply it. This is something I'm going to be talking about now, but yes, you were correct.
So for different sequences of ON, are you able to distinguish whether one is different from the other? Or like for example, if you have a sequence of Pauli measurements, maybe they correspond to the same encoded logical operators. Is your circuit extraction able to show that or distinguish different sequence of measurements?
We do not look into the interpretation of these circuits. What we more likely do is we rewrite. So this is a schedule, and here this Pauli measurement has a very large degree. And what we do is we rewrite it so that it has a smaller degree. That's what our procedure gives. It's not about interpretation.
Thank you.
Okay. And okay, so yeah, this was a pretty good introduction to the next section of this talk, which is kind of what we do, given some kind of so first a Pauli measurement. Here these are local Cliffords, so we can have any kind of, not just ZZZZ. We do this rewrite, which is first just introducing Z spiders and then unfusing this empty spider. Then we find a well-covered MC flow on this diagram. And because there exists a well-covered MC flow, we can always rewrite this into something with small weight Pauli measurements. So in this case, this is the weight for measurements. We rewrite into this, which then by the proposition equals to this, and this is distance preserving. And from this, we can extract a quantum circuit of the following form. So we came from the 422 code to this code, and this was all done using distance preserving rewrites. So the distance must be the same. So this is a 622 code. But the weight of each measurement is much smaller than here. So this was first even weight measurements, which are done quite neatly, but we can also do it for odd weight measurements, in which case we simply just unfuse a spider from the middle, and then that gives you an additional ancilla at the bottom, such as in this case. So what can we do? We can always decompose arbitrary weight measurements in terms of low weight, so weight 1 and weight 2 operations. But this comes at a cost of some ancilla qubits. So just looking back here, what do we do? So for each 2 qubits, so this is kind of this part of the diagram, we introduce a new one. So n over 2 additional qubits. And then here, this is about the number of qubits we get. So at each point, we get a number of extra qubits. So here, these can be described using this function. So in the first case, we get 0 additional qubits. This is this part, if n equals 4. If n mod 4 is 0, which is this case, we get n over 2 extra qubits. Yes, which are given by these ones. And then if n mod 2 is 2, then you get these additional qubits. So this is just n plus 2. And this can be, this is at most log 2n additional qubits. So all in all, we have n plus n over 2 ceiling plus log 2 of n additional qubits to implement an n qubit Pauli measurement. And then what we will do now is just very quickly kind of use these individually on a larger code to extract a larger circuit from some kind of Floquet code, some kind of stabilizer code. So first of all, we write the operation circuit as a ZX diagram. We use the ZX rewrites to rearrange the diagram. So each ZX rewrites on each of the Pauli measurements and then extract a new code. But in two, what we first have to do is produce, so the above rewrites will show you what to do, and then we kind of compose these individual measurements according to the original code. So a little bit more notation. This is the very last bit of notation I will show you. We have this infinite repeating sequence we have kind of mentioned before. This is what it means. So if you have some diagram, infinite repetition is so this and then this and then this diagram. And then we have a couple of rules we can use. For example, we can always kind of bring forward one of these boxes. We can unroll them, so we can kind of, if you only have F, then you can repeat F as many times as you would like, or you can always reorder. So in this case, if you have F and G, then you can bring forward F, and then you will repeat G and F again. So this is, because you do F, G, F, G, F, G, now you do F, and you do G, F, G, F, G, F, which is the same. And now let's look at a specific example. So this is the 422 code, the infinite repetition of this. So first what we do, we look at both of them individually. We rewrite them using the previous decomposition we have given.
I have a question about this FG thing.
Yes.
So if the number, if the weight of the measurement is odd, right? It is possible to have a different number of openings and closings of qubits, right? Like initializations versus measurements. And in order to draw them as like one line, you have to match them to the like you have to find the next segment that is gonna open as many as you have closed before.
Yes.
Is that always going to be possible? I guess you can choose on the next one that you are going to make it an output, the additional one to the odd weight measurement instead of an input. Yeah, okay, then that works, I guess.
Okay, good. Yes, so yeah, you will always be able to do this. But you can kind of see from the fact that there is always, for data or for word lines, if you will, or data qubits, and kind of you rearrange them, and then this will work out well.
But what if
So
your what if your thing includes only one odd weight measurement and a bunch of even weight measurements? Then in order to open and close, you would need to do that first odd weight measurement a bunch of times. But in a normal code, if you have like one of your stabilizer elements is XXX, you wouldn't do XXX 1,000 times before you do the other stabilizer elements. You would want to finish the entire stabilizer round by doing all of the measurements. Example of this might be the star graph code, where you have one high odd weight measurement and a bunch of weight 2 measurements. How would you close that in that case?
So I am a bit lost at this moment. I couldn't quite follow you, but let's talk about this after the talk.
Sure.
No,
Okay.
I'm a bit stressed about finishing on time, which is already done. But yeah, this is a very interesting question. I do believe this is going to work out well, but yeah, let's talk about this a bit later. So rewriting measurements. So what we do, we use the decomposition that we have seen before. We kind of rearrange things, what you can do using, the only connectivity matter rule of ZX. And then, so this is the same diagram we have seen before, just written a bit in a bit nicer way. And then what you furthermore do here is kind of drag these spiders out to here. Then you reorder things. So this is the reorder rule we have seen before, where you can kind of drag this part out and this part out. So this was F, this is G, and then in the infinite measurement, now you have this F before, and then GF, GF, GF. So that's what we do now, that you can see here. And that there is another distance preserving rewrites that you can use to obtain something without any interruption in the data qubits. And then after removing the swaps, you end up with this diagram. So this is now the 6-qubit circuit representing the 422 code. And then you kind of just forget about these initializations of these qubits. But this is fine. And the reason for that is the number of logicals remain the same. So if you think about these things, the number of logicals will be the same, being just this one. So in here also the number of logicals remain the same, meaning that from the 422 code we have gotten this one, and if we kind of forget about this bit, we get the 622 code. And then the number of qubits, sorry. So now we get from an NKD code, an N prime KD code, where N prime is at most M plus M over 2 plus log M2. So this was something, so this M is the maximum weight measurement in the code you have. So in the 422 code, that is equal to 4, but in some other codes, this is not going to be the case. So your scaling can be quite nice with lower weight measurements. So what have we done in this talk or in this paper? We have kind of optimized the Floquetification procedure. So interestingly, our procedure requires less physical qubits than the one given by Teague, which is, it was a very nice realization to see that coming out. So in the future, yes, so optimize the Floquetification procedure is one of the things we want to do. That is kind of, sometimes there is a lot of repetition in the code we obtain, and there it would be nice to remove certain bits of this repetition, but doing so distance preservingly. It would be also nice to consider global properties of codes, or more like kind of consider when you do a rewrite, but you know that the distance, so this would be like a distance at most k preserving rule. That would be interesting to look into. Generalize this whole notion to scalable ZX. So there are other papers that use scalable ZX for error correction in a very neat way, and we also have found a couple of examples where scalable ZX would be a nice way to be used. Another thing which is an interesting future work would be to use the fault-tolerantly calculus, which is kind of another notion of ZX where you don't consider qubits, but rather kind of the Fock space with photons. And GKP codes are error correcting codes kind of fine-tuned for this Fock space. So it would be interesting to consider similar techniques with those. And then decoding, which is a very complicated field on its own. Would be nice to see what we can reason about using the ZX calculus. And then lastly, kind of verifying and synthesizing new codes using these techniques. And that's it. So with this, I'm going to thank you for your intentions, and yeah, feel free to ask any questions now.
All right. Thanks very much, Boldy, for a very nice talk, and it's very cool results. Do we have some questions in the audience? There were already lots of questions. But, do you need to go, Boldy? Was that the reason you were sort of trying
No,
to...
no. I was just afraid of, I wanted to finish on time, which I didn't manage, but that's okay.
Okay. Cole, you have a question?
Yes, thank you for the talk. What is the interpretation of this infinite, like, depth thing? Because it may not converge to like a matrix, right? If you just like take a matrix and multiply it by itself. Yeah.
This is similar to what we have done with Giovanni in the flow, in the paper on flow. So this was the notion of streams. This is very similar, and actually that's where the inspiration for the unroll and the reorder came from. The interpretation of this.
So you're just working in like streams of.
In a sense, yes, yeah. But we are less formal than we have been in the paper with the.
So I have a follow-up question. When you do this like infinite composition, are you interpreting it as like you're introducing new qubits that you're working with, and you have like an infinite tensor product, or is it really just like all on the same qubits and you reuse them?
So in that sense, it's not exactly the same as streams because we don't do tensor products. This is kind of allowing us to disregard a bit before our code, what is it called? Establishes, and kind of focus on the operation circuit. So kind of that's the important part for us, that in this bit, we can assume that our code has already established.
So maybe to give a slightly different perspective on this. So another motivation. So stabilizer codes have these commuting measurements, so the stabilizing group remains fixed, meaning we can kind of very much study them via their stabilizing group or via the encoder, for example. And this is a very, very useful perspective on stabilizer codes. In Floquet code, you have anti-commuting measurements, meaning that the stabilizing group changes over time. And we kind of want to look at this evolution of how the stabilizers change over time. And one way to do that, instead of looking at the stabilizers code, you could either think of it as having a different encoder at each time step, or the other way of looking at it, and this is kind of what the perspective that we're taking, is just look at the circuit that implements this code. So the anti-commuting measurements that take you from one stabilizing group to the next in this infinitely repeating of our measurements. And then the point of this is like we have a 6-qubit code and you have these measurements, and if you only want to have idle, you're protecting your data. If that's all you're doing, then all you're doing is you keep repeating your measurements and check if an error occurred. And this is just if you have 6 qubits and you're just doing different operations on these 6 qubits. And this is an infinite process, and this is and studying the codes through that gives us a very useful perspective of manipulating error correction, Floquet error correction codes.
I have a follow-up question if I'm allowed to ask. So this is a similar notion of like infinite stabilizer codes where you take like kind of infinite tensor product, and then you do like a you have an infinite tableau, but like kind of space-wise. And in this setting, there's like a problem with if you have an infinite depth decoder, then you also want to know that you can also decode infinite depth or do it at the same time. Do you have any intuition about like how you can decode these things in a finite amount of time, or when this is possible?
I think the difference is that we don't do an infinite tensor product. I think you did mention that this is more like an infinite multiplication.
Okay, thanks.
Okay.
I want to give the floor to someone else, but I want to insert a silly comment, which is that this notation for like infinite repetition, like why not use the music bar notation of like repeat this section, and I put like an
So
infinite
actually,
time, like the end part.
That's it. So we've heard that's actually literally where it came from, which Alex mentioned it, and we thought that was a very good notation. Then we kind of put this little infinity here and make it a bit easier to, yeah.
Okay. Clemens, I think you had your hand raised first, so please go ahead with a question if you still have questions.
Yeah, I still have that question about the FG. So suppose your static stabilizer code you start with has measurements F, G, and H. And
Okay.
F has odd parity, and G and H have even parity.
Okay.
The only way to make the extra ancilla you get from the Floquetification of this way, so you have like one, for example, one-weight 3 tensor and two-weight 2 tensors as part of the initial code. Then you could only even that out by stacking the weight 3 measurement next to each other. So doing F, 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 and then GH a couple times. But intuitively, it seems like for the decoding procedure, this might be an issue, because usually, in order to do the decoding, you would need the result from F, and G, and H before you could decide what the correct decoding is for that syndrome. Like, you need to obtain the full syndrome. And presumably, the obtained full syndrome cycle is at least of length F, G, and H together that you will have in this new Floquetified code. So if you want kind of detecting regions that cover every part of your thing, I don't think that if you repeat F a bunch of times, you will obtain these detection regions. And you would need to have some interpolation of G and H.
We kind of start from an already existing error correcting code where we assume that it
But that
has
one's very
properties.
symmetric.
Sorry?
But the one you start from, like the 422 code here, or okay, this is the weight 9 code, but I mean, like the one you go in detail about the 422 code is like highly symmetric in that, well, you have two even weight measurements, right?
Yes.
So this is about the reuse of qubits, right? And the question of how can we reuse them? And what we do is we kind of just pull them through towards the end. This does not have to. You can do FGH. You can just infinitely repeat that. You're just reusing some of the qubits a little bit later. So you after each measurement, you're freeing up the other qubits, and then you can reuse them just the next iteration of your measurement schedule.
But what I'm asking is, like, if G and H would not offer any like docking point for reusal of qubits, like they don't have reinitialization.
Yeah, then you just do identity and pull them past them. You don't have to touch every qubit during a measurement.
So wait, what would that mean? Like, assume that G and H are both measurements that don't have this property of getting additional ancilla via the Floquetification, and only F has this. How would you find a starting point or an end point in another segment to match with the starting or end point in the first segment that you created?
So
I think the point is you don't need to, right?
Yeah.
So that matching is really to deal with the endpoints and to try to get rid of them. If you don't have any endpoints to contend with, then you don't have the problem.
No, but if I have exactly one, like if I have an endpoint from my first measurement or a start point, either one, but I don't have any open start or end points from the other measurements.
Then you take the endpoint from the same measurement, the iteration before.
Yes, but that would mean that you would be repeating the first measurement, that you would be doing FFF.
No, you can do the other measurements in between. You can still take the endpoint of the measurement before.
Oh, okay.
Okay, Sarah?
Thank you for the talk. I have a question about the scalable notation. So if we're using the scalable notation to represent this connectivity between the Z and X spiders, you're implicitly assuming that my understanding is you're implicitly assuming using the CSS code stabilizer generators, because if, let's say, imagining you have a mix of stabilizer generators that is not of purely X or Z type, then how would you use the arrow to represent the bipartite graph?
So my understanding of the use of scalable ZX in the CSS code is that it's used for encoding. Whereas in our case, what we do is the intermediate measurements to make sure that nothing has gone wrong. So it's a different notion of it's a different idea that we had to use scalable.
I mean, I think it's a fair point that it's going to look nicer with CSS type measurements. Like if I have a code that's got pure X or pure Z type measurements, those are going to be representable more easily using scalable. But you can also represent non-phase free things in scalable, but I think it might take some creativity on how to do that.
And another one of my question is about the equivalence way to measure the stabilizers, because, for example, at the beginning you have this O1 to ON, and you could also take the product of two Pauli measurements and get a new Pauli measurement, and this arrangement may give you the same parity checks, but it may give you like a different circuit. I wonder if you have thought about like what happens if you choose a different set of infinite sequence as opposed to a different set? How would that give you a different, like the extracted circuit?
So in the operation schedule, yes, we kind of have Pauli measurements that we mostly have, and then local Cliffords in our case. And then what you might have is if you use a different operation schedule, then what our procedure would do is Floquetify each component individually and then put them kind of together. Maybe in the end you have to do a bit of rearrangement so everything works out well, but I would say that the difference would be the order, which would be similar to the order in which you rearrange the original code. Does that make sense?
Sorry, I didn't understand the order. Do you mean if you...
So my understanding of what you were asking is what happens in the process code when you rearrange these.
Yeah, or you take the product of some of them.
So if you rearrange them, then in the end, you will kind of obtain something which is based on the rearrangement after the Floquetification, because you Floquetify each component individually. So you would Floquetify O1 and then O2, and then kind of compose them together. So taking the product, I am not sure. I actually haven't thought about it, how that would work. Maybe Ben?
Yeah, that might change the weight of your stabilizers, right? So what could happen? So in this Floquetification procedure, I think there's two perspectives at it. There's this, we just extract a circuit for an existing stabilizer code. That's the one perspective. The other perspective is we actually give a new quantum error correction code, namely a Floquet code now with anti-commuting measurements. Either way, there's the question of what qubit overhead do you have? And in our procedure, this is dependent on the largest weight measurement in your original schedule. So if you now take products of measurements, you might get a slightly different overhead. But more generally, the question of when do we consider two of these like process codes, when do we consider them to be equivalent, is actually a very interesting question that I think people have thought about, but it's kind of slightly separate to the work that we're doing here. But it is an interesting question.
Yeah, like I'm not even sure what does the canonicity mean in this case. Like, what do you mean when two codes are equivalent? Because you're already doing distance preserving rewrite. So it seems trivial to say if two codes have the same distance, they're considered equivalent. But I'm not sure if it makes sense to study from a logical operator's perspective. So I don't know. I was just curious if you thought about this.
Yeah, I mean, you might even have very different codes with the same distance, right? I mean, like just the distance is certainly not enough. There might be something to be said about the instantaneous stabilizing groups you have after each measurement, and if kind of there's a relationship between those, because those are also relevant for example, transversal or easily implementable logical gates and your measurements and stuff. So maybe that's something to think about and a way to relate different Floquet codes, but it's a good question.
Thank you.
Okay, we have a hand raised from KH1.
Hi. I just want, well, this might be a shorter question. Can you explain what does this have anything to do with the GKP code? The Floquet, like these distance preserving rewrites.
Currently, it doesn't have anything to do with them, unfortunately. So I do know that Ben and Razine might have started looking into this. So I'm going to ask Ben to maybe expand here.
Yeah. So I mean, this is kind of the future work section of the idea. There's variations of the ZX calculus that can talk about different things, qubits and then continuous variable stuff. And Razine recently put out a paper where they developed this particular ZX calculus, the fucked up ZX calculus, and they've just drawn out GKP codes, what they would like. So the measurement circuits of GKP, of the encoders of GKP codes, and what they would look like. But all of this is kind of being drawn out in ZX, kind of based on very similar, at least, motivations and ideas. So the question is, can we extend all of this kind of reasoning that we're currently doing for qubits? Can we extend that to other variations of the ZX calculus? And I think a really cool long-term goal in that research direction would also be, because the ZX calculus can actually bridge between like these different things. Maybe there's a way of having a more holistic picture of talking about if you concatenate GKP codes with then stabilizer codes on top. Maybe there's a holistic perspective of talking about their interaction and optimizing their interaction together. But this is all future work.
Okay, thank you.
I find it quite interesting that when you use extracted circuits, that you get these like XX measurement that you do twice in a row, and that it's sort of like, I guess this is because like you need this for the distance preservation, and this is very similar to how in the surface code you would repeat all your measurements d times in order to preserve your distance d. So I was wondering, like, is there some sense in which you could apply this rewrite strategy to, say, the encoder of a stabilizer code, and then like Floquetify it in such a way that the distance preserving rewrites would transform as that each stabilizer is measured d times in a row in order to get this distance? Like, is there some sense in which this is like the same idea?
I would say not entirely. So here the repetition is because of the decomposition of the four-legged spider, which needs this kind of repetition because otherwise a measurement error is not detected. And the one you have mentioned is actually, no, in a sense that's also similar, because there you want to kind of repeat d times because of measurement errors, and then you can be certain, or at least with high probability, you can be certain that you know what the actual measurement outcome is. And then your question was related to the encoding, and then could you repeat that?
Yeah, it's not really an exact question. It's more like this observation
Okay.
that I find it interesting that in this set of rewrites, you get something that, like, according to this Lex diagram, looks trivial, like it's repeated to connected X spiders, but like it's like in terms of stabilizer, it's like measuring the same stabilizer twice, which like reminds me of like repeating stuff in the surface code. So I was wondering if there's like any sense in which you could rederive the necessity of doing this for the surface code, or like any other coding.
Oh, I see. That would be very interesting. Yeah, I think there you would kind of need to look into the probabilities of measurements, and yes, of measurement outcomes. Yeah. I think that's a very interesting thing to look into in the future. We haven't drawn kind of an exact correspondence between the two, but yeah.
And then different questions. 'Cause is it like I'm not too familiar with Floquet codes, but is it important for them for these like weight two connections to be local in a certain sense, to be like in a two-dimensional architecture, or and then I guess like your strategies don't say anything about locality in any kind of architecture, right? So that's like, is that something you might want to consider, like when you're like
Yes.
developing codes for like physical architectures?
That's a very good question. And so currently Floquet codes, there is no restriction on the kind of connectivity they have, but we did look into the connectivity we obtain from our procedure. And interestingly, we can do different permutations after kind of each cycle, which gives you different connectivity. And then it raises a question that can you kind of optimize connectivity from this Floquetification procedure? And I do know that Ben is working with some people where he has to go into very much specifics about connectivity. Maybe he can mention that.
Yeah, one interesting thing is, can you find the example of the weight for Floquetified measurement, just the individual measurement? Yeah, there, for example. So, no, if you go up, sorry.
Okay.
Here, for example, yeah. So if you look at the first two pictures, right, you have two weight for measurements. And one way to look at this is we implement the weight for measurements using 6 qubits. Interestingly, the qubits that hold the data shift, right? And before the measurement, the first qubit is just an auxiliary. And by the end of the measurement, the first qubit actually holds data. So what this is doing is moving the qubits that hold data around your chip. And this is then stuff that can be really interesting if you have limited connectivity, because you have this teleportation-like situation in while doing your measurement, in a sense. And this can actually make things fit on chips that wouldn't have fit otherwise. We're currently looking at implementing something on a chip with very limited connectivity. And these Floquetified measurements actually do allow you to do more than you maybe would have done in other ways of thinking about syndrome extraction.
Sarah, you want to ask a question?
So just now you mentioned about performing the measurements, and you're adding the anti-commuting stabilizers into the group. And this reminds me a lot of the subsystem code gauge fixing, because you're also, by doing the measurements, and you're changing the stabilizer group so you can go between different codes. Is there like a connection between the Floquetification procedure and like you start with a subsystem code and you play around with this different set of the operators by using the non-destructive measurements?
I am not familiar with the second part. Maybe Ben can talk about this.
Yeah, so one thing about our definition of Floquet codes or process codes, as we call them here, is that it's incredibly general. It's just via the measurements that you're doing, right? So if you restrict yourself to commuting measurements, our definition of process code generalizes stabilizer codes. If you restrict yourself to measurements that leave the logicals unchanged, then you actually obtain subsystem code. So this generalizes subsystem codes slightly further. But we haven't really thought about how all the knowledge that we have about subsystem codes, and also you guys have been thinking about subsystem codes, right? How this kind of interacts with our research. And I think it would be really interesting to look into that, how these two things could kind of fit together. Because we have a very general perspective on things, and it would be interesting to take some more of the knowledge that we have from very specific codes and how that interacts with what we're currently doing.
Because one thing that we do not understand about subsystem code gauge fixing is we know that by measuring anti-commuting stabilizers, we obtain new code, but we don't know what set of stabilizer to choose such that we would still have a fault-tolerant protocols. But you guys provide a distance-preserving rewrite. So that's why I wonder if you consider the connections between these two types of codes.
I think distance-preserving rewrites more generally can be kind of stretched a lot further of like, look, I have this linear map, I want to implement it. How could I possibly do it? And if somehow distance-preservingly, I can actually synthesize a new circuit, I can do quite a lot with it. So we're currently also thinking about logical state preparation and other things. But indeed, switching between codes or doing these, finding a way of doing these measurements would be yet another thing that you could try to think about using these. They are very difficult to work with. At least we found some. Sometimes it's non-trivial to work with them, but it would be interesting to think about how to do those things distance preservingly. And I'd love to have a chat at some point.
Thank you.
Yeah, we've been going for quite a while, and I don't want to keep you forever. Are there any like burning questions left in the audience? Because otherwise, I think we're gonna call it quits. Okay.
Oh, I have a burning question about their software. Like, are you automating like this process of like PolyWeb using ZXLab or other computer program?
I've been implementing a lot of PolyWeb stuff in physics lately. So, yeah, nothing is that documented yet. So watch this space. You'll see there's a demo notebook there that's appeared in the physics repository that shows some of the PolyWeb stuff that's been implemented. So you can have a look at that.
Thank you.